Welcome everyone. We'll go ahead and get started. Thank you so much for joining us today in this webinar. My name is Sandra Mason-Nix, and I'm the coordinator of the Municipal Solid Waste Initiative of the Climate and Clean Air Coalition to reduce short-lived climate pollutants. This coalition is also known as CCAC. I'll be the moderator on today's webinar. In this webinar, we'll be talking about how waste to energy can be an essential part of the circular economy. For your information, this webinar will be recorded and we will have a Q&A session at the end of the presentation. This webinar, like other webinars hosted by the MSW initiative, are geared towards helping cities improve their waste management and reduce short-lived climate pollutants to mitigate climate change and improve air quality. The initiative is working with its partners to help cities address the waste challenges that generate methane and black carbon. As you can see in this slide, there are proven solutions to these challenges with multiple benefits. One of the solutions is the diversion of waste from landfills, particularly organic waste. Organic waste can be treated to create compost or energy through anaerobic digestion. For other types of materials that cannot be recovered, waste to energy might be one way of treating them. This webinar will discuss how waste to energy fits into the circular economy and can help municipalities deal with some residuals. Before we get started, I'd like to introduce our presenter today, Engineer Carsten Spahn. Carsten Spahn is the Managing Director of Interessengemeinschaft der thermischen Abfallbehandlungsanlagen in Deutschland, also known as ITAD. In English, the German Association of Waste-to-Energy Plants. Since 2007, ITAD represents nearly 100% of German municipal solid waste incinerators, as well as sewage sludge incinerators and refuse-derived fuel incinerators. In this role, he is Deputy President of the Confederation of European Waste-to-Energy Plants, also known as CEWEP, and member of several CEWEP working groups. At the European level, he represents CEWEP as a member of the European Integrated Pollution Prevention and Control Bureau, technical groups for the review of the best available techniques, reference documents for waste incineration and for waste treatment, and is chair of CEWEP's working group, Residues. At the German level, he is a member of the several working groups of the Association of German Engineers, including Working Group 3460, Emission Control, Thermal Treatment of Waste, and the National Expert Working Group KS25, Implementation of Seveso Third Directive, Major Accident Directive for the waste sector. He has also presented the subject area waste to energy primarily at German and European conferences. He often joins delegations to different countries around the world like China, India, Malta, Turkey on behalf of the German Ministry for the Environment, the German Environment Agency, and the German Ministry of Economy, and supports GIZ as well. Engineer Spahn started his occupational career in 1994 at the chemical industry with the German Solvay Group, and first started working in the waste sector in 1995, when he joined a team to project, build, and start operation of a waste management center in the Lower Rhine area of Germany, with different treatment plants, including a waste incinerator, sorting plant, composting plant, bottom ash treatment plant, and a landfill for inert materials. After the startup phase, he became inter alia with head of the waste management department of ASC. And with that small introduction, I'll go ahead and turn it over to Engineer Carsten for his presentation. Okay, Carsten, you're all set. Carsten, you have to unmute yourself. There you go. Hello?
There we go. There was a little problem with the connection, I guess. So thank you, Sandra, for that quite comprehensive introduction. Sorry for deliver such a comprehensive CV. So welcome, dear participants, and thanks to the Climate and Clean Air Coalition for this initiative. And I'm happy to support this initiative and hope to make waste to energy's role in the circular economy a bit clearer to you. And at the end of the session, as Sandra already said, we can have some time for questions and hopefully the right answers from my side. So the slides won't work. That's interesting. There we go. Okay. Sandra already said, what is ETA? The short introduction. We are the German Association of Waste to Energy Plants, representing around about 80 municipal solid waste incinerators and refuse-derived fuel incinerators, and our annual capacity is around 24 million tons treatment capacity. And our members are private, public, and private-public partnership companies, owners. So we represent the whole sector more or less in Germany. So when we start to talk about waste to energy, we have to look back first to the history and maybe summarize a little bit the tasks and aims of waste to energy. So history, look back. In the Bible, incineration is already mentioned. Waste incineration in open fires around 1000 BC in Jerusalem. And if I'm right, I remember it's a long time ago that there's in the Old Testament already says they burned the rubbish at the banks of the Euphrates and Tigris River. So you see, waste incineration has a real long history. But yeah, in the Roman Empire, the Romans also incinerate the waste. But after the downfall of the Roman Empire, waste incineration falls into oblivion. And one of the results was that horrible diseases like pestilence and cholera in the Middle Ages came over Europe. So in the 16th century, the cities decided to collect the waste and to landfill it outside of the cities or use it as a compost, which, that was not a very good idea because they couldn't get rid of the rats and the diseases as well. And the first incinerator, named with the lovely name Destructor, was built in 1874 in Nottingham, and that was the start of a more technical waste incineration, not in open fires anymore. And the first incinerator in Germany was built end of the 19th century, 1894 in Hamburg, with the beautiful name Bullerdeich. You see here the picture of that waste incineration plant already with the stack on the left side. What are the tasks and aims of waste to energy? Of course, sanitation. Volume reduction. People won't, they wouldn't use the landscape around the cities for landfills anymore. The long-run elimination of pollutants from the cycle of materials, a point that becomes more and more important when we're talking about increasing our recycled materials and circular economy. The minimization of emissions, clean air. Efficient use of the energy content of the waste, that is also to see in connection with the climate change and the climate saving potential, CO2 saving potential. Substituting fossil fuels is an important point, and also the contribution to a sustainable waste management through the recovery, e.g. the metals from bottom ash, or the reuse of bottom ash as secondary raw material used in road construction applications, protection walls, noise protection walls, etc. How does it work? Well, here you can see the general principle, the setup of a typical waste to energy plant. You have a waste delivery and storage area. The middle part is the incineration, steam generating part. Then you have the energy recovery part, the boiler and the turbine set and generator. And then most often the biggest part of the plant, the flue gas cleaning system, or I prefer the air pollution control system. Let's take a more detailed look to the incineration here with the waste storage area and the combustion chamber. This is a picture from my old plant from the waste delivery hall. You can see the trucks. We try to keep it clean to make it also, well, a nice place, a nicer place, and not this typical dirty place how most people think what waste to energy and waste to energy plants are. Then we have, of course, the waste bunker, the bunker system, the storage with the cranes feeding the combustion chamber. And then, of course, you have the combustion chamber here, picture of a look through a little window on the grate. And important for the waste incineration, of course, is the input, although you cannot always see what is in. If you have the municipal dustbin, you never know what exactly is in the dustbin, but we have to find, or we have to define some rules about the input. Of course, municipal waste and similar commercial waste is suitable for that. Bulky waste from household may be crushed before incineration. Demolition and construction waste, non-mineral waste, of course. Non-recyclable packaging waste. We all know that we can recycle a lot today, but there are also a lot of compound materials where the ecologic benefit from recycling or the efforts we have to spend for recycling is so high that this is not really suitable at the moment for recycling. We have sorting residues from commercial waste, but also from municipal waste, from MBTs and composting plants, all the impurities. What is not acceptable, a very important part, soil, concrete, asbestos, sand and stone, free-flowing sludges, that is not suitable for great incineration. Bulky metal waste is not, well, metals do not burn. Self-igniting and explosive or highly flammable waste, radioactive or infectious waste. And the most important thing, and a problem in many, many countries I visited before, is that the input is not free of non-combustible waste, and especially very wet waste, wet organic waste with a low NCV, net calorific value. Ideally, it should not be below 6,000 kilojoules per kilogram, because then you have to spend too much energy for drying or for evaporating the water content of the waste. And an old saying of a friend of mine who is the managing director of the composting organization in Germany is that potato soup doesn't burn. And I think that shows very clearly what waste energy can incinerate and what not. So after the combustion chamber, we have the energy recovery part. Here are some technical details. I don't want to go too deep into these details, but as you can see, the incineration temperature is most probably around about 1000 degrees centigrade, and the time that the waste is in that chamber is approximately 1 hour. That is very, very similar to all of the waste energy plants, and that at the end guarantees a very good burnout of the waste if the net calorific value is high enough. And you can produce steam with standard parameters of 40 bars and 400 degrees centigrade. And after that, we can use that live steam in the turbine and generate a set to produce power, or if you have an extracting condensing turbine, you can also extract heat, for example, district heating or for industrial use. But we will see later that the options to get rid of that heat, to sell that heat, to use that heat is a quite important topic for waste energy plants all over the world. So the quick facts in summary: great combustion is, from my point of view, the most proven and widely applied method to treat residual waste and recover its energy. Organic compounds contained in residual waste are safely destroyed. That's one of the tasks. The bottom ash left after incineration can be recovered. We will see later. And also the metals embedded in the residual waste can be recovered from the bottom ashes. Important task too in terms of sustainability. Quick facts about the energy recovery. Energy from waste plants can recover more than 90% of the energy embedded in the waste input. The electricity can produced or is generated around the clock, 24 hours a day, not really 365 days a year, because we need some time to maintain the plant. So between 6 and 8 weeks, the plants are shut down for maintenance. And it's thanks to the renewable part of the waste, a green energy or partly green energy that contributes to climate protection. The heat recovered by a plant can be used for district heating or district cooling, although at the moment it's too expensive. We have to find better ways to use the heat to produce cooling. Industrial processes, and a very interesting thing, especially for islands or countries near to the desert, is the water desalination. We all know that water is one of the important topics worldwide. And for example, we have a very little waste to energy plant in the Caribbean, Saint Bartholomew, where we produce with a little amount of waste, around about 12 or 13,000 tons a year only, very good quality potable water. So there are many other purposes for energy use of waste to energy plants, but we have to find the right place for those plants worldwide. So flue gas cleaning, a quick overview about different setups, small setups or more compact setups like this one here, or a very comprehensive setup with a lot of aggregates, with a lot of treatment steps of the flue gas cleaning or air pollution control with the residues produced here. And another setup, a bit simpler one, but as efficient as the other ones. And they all together produce a very similar set of emissions. And this set of emissions is set here. You can see the pollutants in the left row. You see the German limits from our ordinance on the emissions of waste incineration plants, and you see the operational data as an average of the half-hourly average values. And in the graph below, you can see the percentage of the ELV used on an annual basis, and you see that most of the parameters are used only, 20% or less, significantly less than 20% of the emission limit values. The only exemption is the NOx, the NOx, which can be influenced by the flue gas cleaning system itself. If you have a catalyst, the DNOx system, it depends on the urea you insert into the flue gas stream to influence that value. So, quick facts about the flue gas cleaning system. Emission limit for waste to energy ones are the most stringent in Europe from the whole combustion industry, and the emissions are more or less irrelevant compared to other sources. That's also what one of our ministers for the environment said, and he was a green minister from the Green Party, and we made a study in 2005, and as dioxins and fuels were many years in the public discussion, he said dioxins emitted from waste to energy plants are not an issue anymore. So we have mandatory technology for heavy metal removal, and that guarantees, especially for mercury, which is also in the focus of the Minamata protocol, a safe removal from the ecocycle, safe storage, for example, in hazardous landfills. We will see that if we come to the residues from waste to energy plants. There we go. Here are the residues in a quick overview. Again, I don't want to go too deep into the details, but we can see that from 1 ton of waste, we produce round about 400 kilograms of residues. Most of it are the bottom ashes, 200, 220, 250 kilograms in Germany, depending on the waste inputs composition, some boiler ash, some solid ACPs, APC, air pollution control residues. Sorry for that mistyping. Sometimes you have a kind of police filter at the end of the APC, which is fed with activated carbon. So what can we do? We have, at least in Germany, a very safe disposal and recovery of the APC residues and the bottom ash in an environmentally sound way. For example, we use the APCs to stabilize our salt mines. On the other hand, other European countries have dedicated hazardous landfill sites where they landfill the stabilized residues from waste incineration. We separate and recover the metals from the bottom ashes. This is almost 1% of our recycling target, or our recycling rate in Germany comes from the metals recycled from bottom ashes. And also the mineral part of the bottom ashes can be used as secondary raw material. Yes, only 100 kilograms of the residues are landfilled. That's what I said before. And as we have these salt mines that have to be stabilized, it's also classified as recovery, but that's a specific issue in Germany. So when we talk about waste to energy, of course, we also have to talk about economic key data. I would say that the economic efficiency depends, of course, on the capacity, and the minimum of 50,000 tons per year should guarantee a kind of economic efficiency. But as I said before, in very specific conditions, e.g. on a small island with the need for water desalination, that can be also less than 50,000 tons. The technology installed is quite important. The infrastructural and requirements near to the waste production, to the cities, not the old German strategy, build it far away from the city because people don't want to see an ugly waste to energy plant. That was one of the mistakes we made in Germany, and now we have sometimes the problem to connect waste to energy plants to the heat grid. With the power, it's not a major problem, but with the heat, it could be quite problematic and quite cost intensive. We have, you need a logistic connection for trucks, railway, maybe ship, depending where you are. Near to energy consumers, you need a sufficient supply of waste, of course, without overcapacity, something that was discussed very intensively in Germany. And you can believe me, with 24, 25 million tons of capacity, of course, recycling industry claims that their waste to energy possibly can hamper recycling. But that's a topic for the second part of the presentation. And also the operational availability is very important. When I started my career, we operated waste to energy plants in Germany 7,500 hours a year. Today, we maximize that operational time up to 8,100, 8,200, sometimes 8,300 hours a year, which is a very high availability and of course guarantees also an economic efficiency. So here are some basic conditions, just roughly for you. You can check that afterwards, and also compared costs for building, investment costs. Europe per ton of waste, 500 to 650. Let me say state-of-the-art new waste to energy plants, considering 15 to 20 years in operation. So worldwide, I'm fully aware that the cost can differ significantly. I was in India, for example, where I see that the investment costs are at the lower end, maybe 100 to 150 euros per ton of annual capacity. So these costs have to be calculated very specific for the country you want to build the waste energy plant. You have maintenance costs, which are more or less between 3 or 5% of your investment costs. Not to forget treatment costs, but these treatment costs are also vary with the salary in your country, with the treatment costs for residues or landfill costs for the residues, with your feed-in tariffs for power. So it's very difficult to give here a clear number or a range of the treatment costs, but they are there. It's not for free, that's clear. You need maybe 40 to 60 employees for a big waste to energy plant. That's if you have a more or less automatic control system. I saw waste energy plants in India and also in China, which have significantly more employees than these 40 to 60. You need space for a waste energy plant, and a rough estimation for a big waste energy plant for 5 lines with 150,000 tons of annual capacity, it's maybe 80,000 square meters. And also the net calorific value will influence your capacity. With a low calorific value of, for example, 7,500 or 6,000 kilojoules per kilograms, 100,000 tons at 9,000 kilojoules per kilogram plant will have significantly more capacity. It's 120,000 tons, because the limit is always the energy input in your incineration chamber, in your combustion chamber. So if the net calorific value is lower, the capacity will increase. If the net calorific value will increase, your capacity will decrease. That's for sure. And that's a thermodynamic rule, and also waste energy plants have to follow that rule, of course. So, but what I want to say, or the important message from this slide, is that zero gate fee, what I really hear quite often, is really a myth. Of course, there are countries where the feed-in tariffs for power are so high, with some subsidies in the background, that at the end of the day they can compensate the costs of treatment, but then it's a zero gate fee subsidized by some other things. But waste to energy, it costs money, that is clear, and that is a message that has been told to people outside a waste to energy plant. I remember some municipalities, for example, in India again, where we had very hard discussions about the zero gate fee policy, and we compared it a little bit to the wastewater treatment in India, where at the beginning it was almost impossible to introduce a treatment fee for wastewater, but today there are treatment fees paid by the municipalities, and maybe that's the way how we can deal also with the gate fees for a proper waste to energy plant. So energy efficiency and climate protection potential, that's one of the second tasks, or the second aims of the Climate and Clean Air Initiative, climate protection. That's, for example, the energy production in Germany. And you see it differs always a little bit between heat and power, depending how much heat you can sell, how warm or cold, for example, was the winter, but the sum of the total energy produced in Germany in the last years has increased a little bit. And if we calculate the greenhouse gas savings from that, you see, of course, there is a burden. 1 ton of waste creates 1 ton of CO2. Round about half of it, or less than half of it, is fossil content. So at the end of the day, the specific emissions are almost 400 kilograms per ton of waste. So 9 million tons on the burden side. But you also generate credits. In Germany, we have still some coal-fired and gas-fired power plants, and if you calculate the CO2 credits by using the substitution factors, you see at the end of the day, the German waste energy sector saves 7.25 million tons of CO2 just by substituting fossil energy sources in our country. This is quite a lot, but not as much as we save in another direction. Here, sorry, I missed that. We also calculated And not only we, it's coming from the Dutch Ministry from the Environment. We compared the different specific costs for saving 1 ton of carbon dioxide, and you see that waste to energy is has by far the lowest specific CO2 saving costs. But another point is quite important. That's what Sandra said in her introduction. If you want to get rid of your landfill and replacing landfill with an efficient waste to energy plant, you can see that the amount of CO2 emissions that you can save, the methane, which is 25 times more dangerous for the climate than CO2, is really huge. If you improve an old existing waste to energy plant by a new efficient plant, there is still a benefit for the environment, but replacing landfill, this is really a huge one. You can save almost, almost 700 kilograms per ton of waste CO2 if you replace that, and that for years. And so that's the reason why, for example, in Germany, the waste management sector was one of the first big contributors to climate protection in Germany. So quick facts again, energy from waste is about 50% renewable. Thanks to the substitution of fossil fuels, we have a nice economic and ecologic effect by saving CO2 emissions. Most benefit comes from the methane mitigation. If replacing landfill, CO2 avoidance costs are low. And also interesting, there are some tools in the ETS. I was always a fan of this clean development mechanism. Unfortunately, we failed to have an agreement with the part of our EPA that we can help some countries with those CDM projects, because till today, the waste to energy projects are not really very popular. Let me say popular is maybe the right expression for that. So something we can work on. Okay, that was no, it was not a very quick, but that was the overview about the technical background. What is waste to energy? How does it work? What are the benefits? What are the emissions? And now let's come to the waste to energy in the circular, waste to energy role in the circular economy. Let me start with the vision. And I think it's very important to have visions, because that is our aim. This is what we can ideally reach if we really live with the rules of circular economy. But this is a vision. I hope, I think that no one believes that we will reach this circle one day with 100% having materials in that circular economy, because reality looks a bit different. Of course, we need energy and raw materials to design, to manufacturing products, to distribute them, but then there is a first side stream that goes into the anthropogenic deposit. For example, in buildings, materials, not waste, materials stay maybe 20, 30, 40, 50, 60 years in buildings, technical buildings, before they come back as waste someday. And so they have been substituted, and in an endless circle, they cannot be substituted in the next years. So you have to replace them by maybe raw materials. On the other hand, you can substitute some parts, of course, by recyclates. You have the collection and the recycling, but there are a lot of unwanted substances in the recycling scheme, in the recycling sorting plants, the rejects, unwanted materials coming from chemical legislation, things like POPs, for example, heavy metals. So they have to be sorted out. And for those materials, we have the waste to energy, and waste to energy not only in terms of municipal solid waste incineration, it's also about co-incineration in cement kilns, maybe coal-fired power plants, not the sector of the future in Germany, but they also contribute to that waste or to that reality in waste to energy sector in Germany. And of course, you need also hazardous waste incinerators for very specific high polluted waste or infectious waste. And at the end, you also need the landfill. You need the landfill for the residues. You need the landfill for mineral waste, non-combustible waste. So this is reality. And of course, we have to minimize maybe that what is going to as reject or as residual waste to that waste to energy. But at the end of the day, this circle cannot live without a sink, a polluted sink. It's comparable to our body. We need our liver, we need our kidney, and maybe the liver is the better example because the liver is on the one hand cleaning our blood, on the other hand producing a lot of energy for our body. So maybe our business is a little bit the liver of the circular economy, so it's a basic pillar of it. That circular economy and also the pollutant sink waste to energy is not easy to achieve. You can see that on that graph. It shows the current status of European countries, and in gray, the gray bar is the landfill fraction, the red bar is the waste to energy, amount of waste going to waste to energy. The yellow one is that fraction that goes to composting plants, and the green one is the recycling plant. And in the big green bar is the recycling target for 2035 according to our new legislation, the Circular Economy Package, the review of the Waste Framework Directive in Europe. And the interim targets 2025 and 2030 are also in there. So, but you see a lot of countries at the moment will fail to even come near to that target. And to be honest, also Germany, which is on the very right side, will have maybe problems because one thing is not in that graph, and that is that the calculation method had changed a little bit. So today, or in the last years, we calculated the recycling targets or the recycling rates in Germany at the input of the recycling and treatment plants. So now we have to calculate it at the output. So all the residues sorted out in the pre-treatment phase are not counting to the recycled amounts of waste. So that will be a very interesting development, how these figures will be after changing the calculation method. And first voices, first studies say that even Germany will go down at the moment to maybe 50% or 49, 48%. Some say 55. We will see what our first statistic according to the new calculation scheme will show us next year. So another important thing is the maximum landfill target in 2035. Only 10% of the municipal waste should be landfilled. And for some countries with less developed waste management system by now, which are Malta, Greece, Romania, Croatia, and Cyprus, they are allowed to fulfill that target in 2040. But it's a very important task, but it's also a long time to go, and we have to spend still a lot of efforts to reach that targets in Europe. So, quick facts on waste to energy's role in the circular economy. Thermal waste treatment is a cornerstone of waste management industry and an integral part of the sustainable resource management. That's what I showed with the reality of the circular economy graph. I think that hopefully is clear. Waste to energy acts as a pollutant sink. It guarantees an environmentally sound and long-term disposal security. Guarantees a long-term disposal security, also important. If some of you might have seen the pictures of waste stored in the streets of Naples and south of Italy, or the pictures of Lebanon where the waste is stored 3, 4, 5 meters high in the cities because the landfills are not able to accept the waste anymore. This is also a very important task, and it should be payable for the citizens. It's a sustainable contribution to resource efficiency through thermal recycling. That is something that was discussed intensively in Germany, if this is really recycling. But of course, it's a kind of recycling. Of course, it's not true recycling, no material recovery, but energy recovery and some material recovery. I told you about the metal separation from bottom ashes and slags, and the production of high quality granulates that can be used in applications outside landfills, road construction, noise protection walls, other walls. So in combination of both, and so that's the reason why we call it thermal recycling. And the resource waste, and that's, I think, the important message, can only be used efficiently and sustainable if all treatment options, material recycling, energy recovery, and landfill are properly combined based on a proper segregation of waste at source, because every different treatment step needs specific input criteria, input quality, and the easiest way to achieve that is to keep your different waste streams, for example, the biodegradable waste, separated at source. So, but how to establish? That is not so easy. We saw it in India. We had discussions in China, in Malta, also in Eastern Europe, even today in Southern Europe, in Italy, in Spain, in Portugal, south of France. Still in Germany, if you want to build new plants or replace old plants by new lines. Well, of course, in countries with a less developed waste management system or technical waste management equipment today, a proper waste segregation is important. A safe and reliable collection is important. We saw that in some countries of the world, municipalities are responsible for collecting the waste with some kind of municipal transfer stations, but from then some private companies are responsible for delivering the waste to the waste-to-energy plant. Unfortunately, those companies are paid by weight, and so the best option to raise the weight and to earn some more money is to put some water, some stones, and some sand and mix it with the residual waste. That, of course, have a huge impact on the net calorific value. Stones and sand and water does not burn. Sand does not burn, water does not burn. So these waste-to-energy plants have a huge problem with the input quality of the waste, and they're operating more or less all the time outside the design parameters of the waste-to-energy plants. Second important part is the economics. You need a reliable business model for waste-to-energy. If you lose 8 or 9 or 10 euros or even 2 or 3 euros per ton of waste because your gate fee is not sufficient or your business model is not sufficient, then you won't have money for a proper maintenance, and that again has huge impact on the third point, on the plant performance and the environmental aspect and the public perception. So realistic conditions of operating contracts, build, own, operate contracts are very famous and popular in the world now, but at the end of the day, I'm a little bit doubtful if all these contract conditions can guarantee the survival of a waste-to-energy plant for an operational time of 15 or 20 years. So waste-to-energy plants performance is always important people will only trust you if you have a good operating performance and a high environmental performance. That will increase the fourth point, the public perception. And also important is a transparent plant operation. Show the people how low your emissions are. You need an appropriate permitting and monitoring. Also, the competent authorities have to be skilled so that people can trust that the waste to energy plants are monitored properly by competent authorities. If they don't trust the operator and don't trust your competent authority, then you will have a problem. So what are the strategies for implementing waste to energy? Segregation of waste at source is essential. That's what I said before. Maybe in some specific cases in parts of the world where you have dry and rain seasons, pre-treatment, pre-drying if necessary to meet the design quality of the municipal solid waste incinerator, and avoid the deterioration of long-term capital investment. That is very important. If you have no money, you will lose your whole investment. We saw waste to energy plants after 2 years of operation, the capital is, or the investment costs are almost lost because the plants are in such a bad shape because no one spent only 1 pence for maintenance. So maintenance and replacement strategy, 25 years of operation is it's an aim. It's maybe not easy to reach in every region of the world, but it should be at least 15 or 20 years. Establish transparent emission measurement systems, SEMS, continuous measurement at all times, and convince the public by publishing the environmental performance. A regular and stringent monitoring of the plants, that's what I said before, also to increase public acceptance. To have an exchange of experience, to create an exchange of experience between different operators, contract partners, but also competent authorities, and also important with your neighborhood and with the opponents. It's better to talk with them than just ignoring them because they have fears. They still believe the old prejudices and stereotypes about waste to energy, maybe. So God Recycle, Devil Burns, we come to that, but in one of the next slide, is still very popular around the world. And we all know that the NGOs can be a very tough partner in that discussions. But at the end of the day, I think with a proper working plan, you have some good arguments to convince them. Establishing specific national technical standards, also a very important thing. In Europe, we have the best available techniques, the BREF documents revised every 8 years, and then they have to implement it into national legislation in the next 4 years. Including monitoring and auditing routines, I think that is also quite important to convince people that these waste to energy plants are not only performing well, they are also monitored very well. The last point are the barriers. I think that is also nothing new. You have, compared to landfills, high investment costs. Quite often you are missing energy users, especially for heat, but also power can be a problem. I talked to friends in Ireland operating a waste to energy plant, and they said, yes, well, when the wind is blowing and the sun is shining, we have so much renewable energies in the grid that we are not allowed to export power to the grid anymore. So we have to switch off our turbine. Unfortunately, we have no possibility to use the heat at the moment, so we're desperately looking for a heat sink, heat users in Ireland. Public acceptance, I said that before. God Recycle, Devil Burns ideology is, well, unfortunately still common in many parts of the world and in many NGOs. these are pictures of that ideology. You see that dirty, ugly plants with a lot of black smoke coming out. Although most of these pictures are not really a waste to energy plant, these ideology will be fed by those pictures. So the best thing what we can do is have a transparency from the start of the project, from the planning phase through the permitting phase, the building phase, and the operational phase. An active communication with your neighbors, your residents, your local authorities, with the politicians is very, very important. And especially politicians, they listen to the people of your neighborhood. And so you should listen to those people too. Take their fears and worries, take them, listen to them, and find ways how to convince them that these fears are maybe a little bit old-fashioned, that waste to energy is clean, is safe. And one or very important are third-party advocates, lawyers, people of public, which are present in the public, lawyers, doctors, politicians, whatever, prominent people, some VIPs, whoever you can find, which are convinced that waste to energy can help. You need people that other people trust, and so that can help a little bit. And if you have this perception, then something went wrong. This is from a Belgium newspaper, I think it's 20 years ago, where one of the plants really had problems with the emissions, and then they had a nice public relation campaign, but the next day they produced the death as a new waste to energy press officer, no negative impacts through waste to energy. So this can show how tough this business or sector can be. So, but at the end of the day, we hope that we can convince people that energy from waste is clean, safe, and maybe it's a little bit cool also for the kids, that they can see that waste that cannot be recycled can be used to produce energy or power. And as a synonym, you can see here the power plug in the waste bin, something. I think it's a nice idea, because that is how people can understand what waste to energy really does today. And it can be good looking. If you compare it to the pictures I showed before from some NGOs, you see that also the design of modern waste to energy plants can be quite interesting, and not these old ugly plants. And so that's it. Thanks for your patience. And yeah, we think that the old CWAP slogan, waste to energy and recycling, goes hand in hand. That is the important message that we try to distribute all over the world. Waste to energy does not hamper. We guarantee recycling. We are the pollutant thing, and that's our role in the circular economy. Thanks again.
Thank you, Engineer Swan, for your presentation. It was very informative. So now we'll take time to for some questions. We only have about 5 minutes for questions.
Maybe 10.
Okay, 10. Thank you so much. So we have some questions already. So I'm going to go ahead and open the mic for Julio. So Julio, if you can go ahead and make your question. Julio, can you? There you go. Julio?
Okay. Can you hear me?
Yes.
Yeah, I can hear myself. Yeah. So I had two questions. The first one was more regarding capacity and like it's of the scale of waste to energy technology. And I think you mentioned like 50,000 tons per year as a. Excuse me. I think I have this. Okay. I think this is better right now. Yeah. So yeah, it's about the capacity, and you mentioned 50,000 tons per year as in order to be economically. I don't know. You meant economically viable or simply that in order to be, you mentioned efficient, but I wanted to have a more idea if less, it can be reasonable to make an investment for this technology. And there, the other question was about, like you mentioned, anthropogenic deposit. If you could explain a little bit more about the concept, that would be very helpful. Thank you.
I didn't get the second question. The first question was about the minimum capacity that gives a kind of economical and ecological efficiency of the plant. That I understood, but the second one I didn't get. Sorry, can you repeat it?
Yes, sorry. And when you were explaining the circular economy idea and like how waste or residuals can go there, you mentioned that there is like this anthropogenic deposit.
Mm-hmm. Yeah.
Yeah.
Okay.
Elaborate on that idea.
Okay, so let's start with the first question: minimum capacity. Well, we, you know, when you see the setup of waste to energy plants, you know that there are quite high investment costs. You have different aggregates for, especially for the air pollution control system, and so the smaller the plant is, the higher the part of the air pollution control and this expensive part will be. So the specific costs to treat 1 ton of waste will increase, and the bigger the plant is, the lower the specific costs are. That's a rule. That's not a rule only for waste to energy. That's a rule that is for many other business sectors. So, but on the other hand, also the efficiency of the plant depends on the minimum capacity. You have self-consumption of the plant. You need a small turbine for your self-consumption for your electric devices. So, and then at the end of the day, if you want to still export some money and to have a benefit from your feed-in tariffs, you should be over your electrical consumption with that part. So, and we think, and we saw that in the past, for most of the countries, 50,000 tons annual capacity seems to be the break even where we can have boundary conditions for the economical efficiency of a plant, and also from the energy efficiency point of view that makes this operational the operation of the plant reliable. And yeah, I think there are other examples. I told you about the small waste energy plant on the Caribbean island that produces potable water. It has only 12,000 or maybe 18,000 tons annual capacity, but it can use all the steam produced, no turbine, to produce potable water, which is urgently needed on that small island without groundwater reserves. So it depends always a little bit on your specific boundary conditions. If it's now 50,000 tons, 30,000 tons, maybe 60 or 70,000 tons. That was, I hope to make that clearer now to you. Second question was about the anthropogenic deposit. It means that in an ideal circular economy, you produce a material, you distribute it, you use it, you throw it away as waste, you recycle it, and then you have a recyclate that can be used as virgin material again in the circular economy. That's the theory. But in reality, there are a lot of materials which are used for a very, very long time. So they are more or less in an anthropogenic deposit. They don't come, they won't come back very soon to that circular economy. Most of the materials, if you see packaging waste, biogenic waste, our typical residual waste, the one circle is very short, less than a month sometimes for packaging waste. You buy a product from the production till the producing waste is sometimes only a few days or weeks. But if you have construction materials like stones, concrete, mineral products, windows, everything what is used in buildings, it's stored for maybe 25, 30, 40 or 50 years in building if you have sustainable buildings. So, and then this material comes back to the circular economy one day, but not today. And this is also a problem because most of the materials that coming back to the circular economy from that sector are produced 50 years or 40 years ago, under different rules of chemical legislation, and they very often contains a lot of harmful substances or substances which we defined as harmful today, but which were harmless 40 or 50 years ago because we didn't know, like asbestos or POPs, for example. And this makes the anthropogenic deposit a little bit problematic for the circular economy.
Great, thank you. So we have another question from Bishwas. I'm going to go ahead and unmute your microphone so you can make your question. Bishwas, are you there?
Yeah, hi.
Hello.
Thanks a lot for the presentation. My question is regarding the average gate fees. What is the average gate fees in Europe versus other developing countries in your experience?
That's a very good question. I hope to find a good answer for that, because of course gate fees are very much, or depends very much on the boundary conditions of your economic boundary conditions, on the technique installed, on the level of environmental protection that you want to achieve, and also on the investment costs, the salaries, the disposal costs for your residues. But to come to the point, in Europe, we calculate with treatment costs, which are more or less the gate fees, between, let me say, 60 up to 100 euro, to give a wide range, and the average maybe is 70 or 80. But this is full cost. Sometimes operators have different contracts, so of course they have some waste that is coming in with a gate fee of 90 euros, some waste is coming in with a gate fee of 60 euros, and at the end of the day, the average again is between 70, 80 or 90 euros, and it's an open market, so it's all the typical market mechanisms are in place in Europe, at least with waste for energy recovery. For waste for disposal, it's still the obligation for the municipalities to treat that waste, but for waste for energy recovery, it's an open market. I can tell you about other countries because I was active in India. There we have a zero gate fee policy, but the two of the operators I visited in the capital area, they lose between 4 and 32 euro per ton of waste by treating the waste, because they have no gate fees. So on the other hand, you can say, to have a sufficient gate fee, including the feed-in tariffs, which are quite interesting in India, you need in India maybe 15, 20 euros for sufficient waste treatment and to have an economical situation of the plant that guarantees the survival for the next 15 or 20 years. In China, there are gate fees, but honestly, I don't know the amount of money they charge at the gates. But clear is that waste energy is not for free, or you have to find other subsidy rules. But I think the best way to tell the people that you take care of your waste with high environmental standards, it's that there is a sufficient gate fee.
Okay, thank you.
Yeah, thank you very much.
Okay, so I think we have space for one last question, so I'll go ahead and unmute Gerardo. Gerardo, are you there? Gerardo?
Hello, can you hear me?
Yes, go ahead.
Yes. Okay, well, first of all, thank you very much, Sandra and Karsten, for setting up this webinar. I think it's very important, and I think it's a pending issue to to spread information, like solid information about waste to energy technologies, not as the only solution, but as part of an array of options that countries need to look at. So thank you for that. So I have many questions, but maybe a couple is, I mean, thinking about how these technologies can be start to be implemented in developing context. So source separation seems to be a key factor for success, and source separation definitely in Latin America at least is not really still very widespread. So what do you think about thinking about like mixed schemes where you can get started with some municipal waste source separated, but also working with industrial waste? I don't know if this is not something that it's normally done. It can be done to have a mix of municipal solid waste and industrial waste. That this, I mean, the relation can change over time in order to increase the participation of municipal waste. But I don't know if that's something that it's too complex. I mean, when it comes to a technical and engineering point of view, you have to design the plant for a certain mix, or there is some flexibility to adapt the plant to different feedstock over time. A second quick question: you mentioned that the energy from waste is 50% renewable energy. If you can clarify that that concept. And the third one, sorry, just in terms of other thermal technologies. I mean, you mentioned great combustion as the main one, the most robust, it seems, but we are constantly receiving providers of pyrolysis, gasification, plasma. So there are many other thermal technologies. So what do you think about those being used for municipal solid waste? Thank you so much.
Thanks for these very important and interesting questions, and I'm really happy that you ask all of them. So let's start with the input mix. Of course, it makes sense if you have a very low calorific value in your municipal waste that you mixed it with suitable industrial waste. That's why I showed you the picture at the beginning, which are the do's and don't, which are the acceptance criteria for the waste input. And one part, of course, even in Germany, is industrial or commercial waste that is comparable or similar to municipal waste. And you are fully right. If you begin to establish a waste management system, waste to energy is not the first option, and you are also fully right. Waste to energy is not the only option. It's one part of the solution. It's your pollutant sink at the end. But if you begin with source separation and treating separated waste with composting, with maybe proper landfilling, with recycling, these are the first steps, or even retrofitting your landfills, having safe landfills at the beginning, that are the first measures. But if you decide then that you want to save land space in a big, or you have no more space in your, especially in the big cities, you come to that point one day, you need an alternative for the landfills. And then waste to energy is the option. We saw it in Delhi, we saw it, for example, on Malta Island, where you have less space than everywhere else in the world if you're living on a small island. So then you have to think about waste to energy, and then of course mixing waste from the industrial sector or from the commercial sector can be a solution to improve the quality of your waste. In Germany, we have these so-called dedicated RDF incinerators linked to industry, so they can accept a higher net calorific value. They have some technical modifications, for example, a water-cooled grade, so the bandwidth of net calorific values is even wider than a normal grade incineration. They can accept between maybe 6 and 16,000 kilojoules per kilogram. A normal grade incineration has a range between 7 and maybe 11, 12, 13,000 kilojoules per kilogram. So that can be, of course, a solution. That was question 1. I hope that I answered that well. The second one was about the 50% renewable part of the energy. Well, that's quite easy. If you look to the composition of municipal waste, you will find that in most of the developed countries, even if you have source separation of organic waste, of biogenic compounds, you still have residues in your waste, polluted paper, what else, hygienic polluted waste, which are still guarantee an organic part in your municipal waste that is 50% or higher. But that's for industrial countries. I will agree with you that in other countries, the organic part will be even higher than 50%. I can remember that we started in Germany with our studies with a 70 or 72% of our organic content in our municipal waste. And thanks to the source separation of bio-waste, we are now at 52 or 53%. So, and at the end of the day, if you have 50% organic content in your input, you have 50% of fossil-based waste, and that means that also your emissions are 50% renew, or not your emissions, that your energy produced comes 50% from renewable sources, according to the definition, of course, that the renewable sources or that organic fuels are not contributing to the climate change potential. So the last question is the best question, I think, because you are fully right. A lot of companies and people are promoting these advanced technologies. And from a German perspective, I can tell you, we tried almost all of them, gasification, plasma, whatever. And we made the big study together with our EPA and the University of Aachen, which is very famous for the technical department for thermal processes. And the conclusion at the end was, yes, advanced technologies like plasma and gasification, pyrolysis, they can work, but they can work only for very specific and well-separated waste streams, but not for mixed municipal waste. All projects that try to treat mixed municipal or mixed residual waste with these advanced technologies, they failed. The last big project was in the UK. It was called Teesside Valley. It was a gasifier producing, thanks to the subsidy scheme in the UK for gas produced out of waste, a lot of subsidies, the so-called ROCs. They lost $1 billion after a major technical issue. So I think from our perspective, it's clear new technologies can work for very dedicated waste streams. After separation, high calorific, very pure, without any impurities or heavy parts that could hamper the gasifying or the pyrolysis or the plasma. It can work, but they are most probably much more expensive than typical grade incineration, and they are definitely not a proven technology. The only technology that seems to work on the first look are the Thermoselect technology that was developed in Germany, banned in Germany, and now and today is still working in Japan. But after visiting the thermoselect plants in Japan, they said, okay, we will be so happy that we can shut down the plant within the next 5 years, because then we don't have to fulfill our contracts any longer, because at the end of the day, we spend too much money. We will lose, or we are losing money with that kind of technology, using oxygen, pure oxygen, for example, for high temperatures in the gasifying parts of the plant. So at the end of the day, the answer is very clear. Advanced technologies are not suitable for the treatment of municipal solid waste.
Okay.
Thank you so much.
Thank you, Gerardo, for your questions. Okay, well, we have gone beyond the time allotted, so let's go ahead and finalize conclude the webinar. Thank you so much, everyone, for your participation. Before we conclude, actually, I would like to inform you that the webinar was recorded and will be posted on the Municipal Solid Waste Knowledge Platform of the MSW initiative, and this is the web link. So www.wasteccaccoalition.org. And again, thank you so much for joining. And here's my email address if you have additional questions. Please complete the exit survey when we complete the webinar, and please register for upcoming webinar. Lastly, on behalf of the CCAC MSW coalition and then in the MSW initiative, I would like to give a big thanks to Carsten Spohn for his time preparing and giving this presentation and for answering all our questions on this very important topic. I hope everybody was happy with it. And again, thanks and have a great day. And I hope you will join us in upcoming webinars.
Yeah, thank you.
Okay, bye-bye.